All right, so welcome everyone. It's good to see you. And this is another part of the lecture. And this time we're going to talk about game theory from the tragedies of the commons to emergent collective behavior. And as always, we're going to start with an interactive part. And so I will ask you, what do you know about game theory? Yes? That's quite a lot of information that you already have. So I guess it will be hard to add something, but anyway, there was also a hand to Nash. What does it mean? Nash equilibrium? Right. And that's why it's an equilibrium, right? Good. Any other points? Yes? Game of life. Yes. I think one could probably count it among game theoretical problems. The cell law automaton, but a lot of games are actually of this kind. Yeah? Can you speak a bit louder? Yeah. Okay. Is game theory about chess or card games? Well, potentially, yes, but most scientists have not actually spent much time on looking at those games. But a lot more simple games, typically. So what else might be interesting? Yes? Cold War. Yes. When has game theory been invented, by the way? No, that was during World War II, I would say. Any more points to be made? What about competition versus cooperation? Does that sound like an interesting subject? Yeah? Okay.
I don't know if it's also in the area of but I think in psychology, one of the most studied cases is the common goods game, where
common goods, yeah.
You have two modes, one without punishment, or where participants can't punish other participants, and one where they can. And basically, in the modes where they can't, the collaboration is decreasing bit by bit, and so one is basically trying to offer something, and with punishment, surprisingly, the cooperation goes up.
I think I don't need to give my lecture anymore after this. Sachit, are there also some comments or questions online? Okay. Yeah, thank you very much. That was a good start, I would say. And today we'll talk, yes, about game theory. There are actually different kinds, like strategic, behavioral, and evolutionary, all of course somehow interconnected. The behavioral doesn't make those strict rationality assumptions, it just wants to know how real people behave. And the evolutionary is interested into temporal evolution. And in fact, that has also been of interest to me always, I must admit it. So when I read the first book about game theory, I was a bit disappointed that it was all about optimization and minimax theorems and stuff like that, but there was no dynamics at all. And I thought, no, is that real life? Anyway, so we'll learn about evolutionary game theory here. I'll learn about imitation, agent-based models, coordination, cooperation, Homo socialis even. And the third time also something about social norms and conflict. Okay. Yeah, overview. So one of the questions of interest is how to reach cooperation under social conditions that promote defection. Defection means uncooperative behavior. How do behavioral conventions come about such as people tending to walk on the right-hand side? In Japan, it's actually the left-hand side, I believe. And in fact, it doesn't matter. It's just what matters is that people coordinate among each other. Right? And then how does moral behavior emerge? Why are we social, and why do strangers often cooperate also with each other? And what causes social norms or conflict? All right, and with this, we're going into the main part of our lecture, and left the overview part. And in fact, we're looking into two prime examples of social dilemmas, which are very old, I would say thousands of years old. I mean, since the existence of humanity, we do have these kind of problems. And some of them have been solved, and some of them we are still struggling with, as we'll see. So one of those cooperation problems is called stack hunt game. It's about hunting stacks or rabbits. Rabbits are small, you can hunt them by yourself. That's the idea, narrative, as people would say. But if you want to hunt stacks, you typically can't do that by yourself, but you need to cooperate, right? And so you basically have to take this decision. And this will be translated later on into a so-called payoff matrix. And payoff measures success in game theory, typically. And this is the public goods game, which was already mentioned. You'll probably know it all if you have lived together with other people in a shared student apartment, you know, then somebody needs to clean up the kitchen, and typically has to be shared among the people living there. And then the cooperators do the work, the free riders benefit. They reap the fruits of that cooperation without contributing. And yeah, so basically the public goods game is about a situation where the cooperators contribute to that public good and the free riders don't. But then in the basic version of the public goods game, the resulting good that is being created through cooperation will be shared among all the people. I mean, basically, free riders get the benefits for free, and the cooperators have to make a big effort in order to get that benefit, right? So that can imagine that this creates temptation to free ride, and cooperation is in a sense risky. And yeah, I don't even want to remember when I moved into such a shared student apartment in Göttingen, where I studied a couple of years back, actually quite a few years, how the situation of the kitchen was at that time. But I managed to come up with a mechanism that really changed that situation dramatically. And it was something like a watch. I had all the names of all the people living in on that watch. And it was moving forward from one person's name to the next person's name, and every week basically that watch moved on to the next door. And that really changed things. So what we're going to talk about here is about social and other mechanisms that will turn a social dilemma situation into a situation where cooperation comes about. I wonder whether I still have a picture. Anyway, funny memory just came up. So, I mean, I said we do have these problems still. Even after thousands of years of being confronted with those social dilemmas, they're still not solved completely. So we have environmental pollution, it's one of those problems. We have overfishing, we have climate change. And all of these outcomes that result from a failure of cooperation to come about, or an erosion of cooperation, these are called tragedies of the commons when it comes to a public good, like a shared space, a park. For example, maybe in a good condition, nice and clean, or maybe polluted if people just drop the garbage after having their lunches or whatever, their picnic in the park, and after some time it looks terrible. And a similar situation happens to nature and environmental conditions. So over here, the forest is gone more or less, and over here we still have a lot of trees. And here, what you need to know is there is a border between Haiti and the Dominican Republic. And obviously there are two different kinds of managing that resource of the environment on one side of the border and on the other side. It shows that tragedies of the commons can come about, and they often do come about. But also there are ways to overcome that problem. And, some countries have managed. And this is in particular what game theory is about. And here is a formal definition. So game theory is a mathematical discipline providing a set of analytical tools and solution concepts which have explanatory and predictive power in interactive decision situations when the goals and preferences of the participating players are potentially in conflict. When we were young, we had to do these things to repeat those sentences. Anyway, so it's a lot about understanding social interactions, in other words, and this has been invented back in 1944 by John von Neumann and Oskar Morgenstern. Do you know John von Neumann? So what else do you know of him?
He was a famous mathematician who studied protein.
So what then is he doing in the field of economics and social behavior? What else was he doing? In fact, you all have computers that are based on what is called the von Neumann architecture. These are computers that run on zeros and ones and operate them in a sequential way. And only now we're getting a new kind of computers that is called quantum computers that work in a completely different way. But hey, 80 years. That's an amazing amount of time. And he also is famous for some work in physics and quantum physics, in fact. I mean, he even did quantum. I think he was a genius, really. And obviously, in war times, resources were short, now we are also again talking about resource shortages. Anyway, so that's why people were interested in coming up with optimal solutions. And in that context, also game theory was invented. And in fact, as you say, this concept of the equilibrium of threat, of mutually assured destruction of in nuclear times, that was one of the game theoretical concepts that has worked for quite some time. I wouldn't fully rely on that for the future for various reasons. But yes, this thinking came out of game theory. One of the reasons why we should be more careful about it is that there have been a number of incidences where nuclear war almost started by accident. So if you want to ensure that nuclear war would never happen, then these kind of accidents obviously should never happen. So that's one of the reasons why we need something better. It's just too dangerous. But again, people look into game theory, new kinds of strategic thinking. And we'll now turn towards evolutionary game theory. That was invented a bit later. And about coordination and cooperation. And here's a paper that is related. I think you just chose that paper to be presented. And this paper is basically about trying to come up with an equation that describes the change of the distribution of behaviors in time. So this P is the distribution probability of behaviors I in time. A distinguishes potentially different subpopulations, men, women, whatever. If there's a reason to distinguish at all, in many cases we don't do that at all, but mathematically it's possible. And so basically, the probability of finding behavior I at time t is changing through people who have another behavior I prime at time t, and then change from I prime to I with a certain transition rate W. And obviously, we can sum up over all the different I primes that come into question. And then on the other hand, there's a reduction by those people who are currently showing behavior I and are changing to some other behavior I prime given I. And again, we can sum up over the different items. Okay. So there's change is given by the inflow into I minus the outflow from I, and the inflow is given by a sum of transitions and the outflow as well. Okay. Clear? It's called the master equation because it masters this kind of processes. It's not terribly complicated, but it needs a little bit of time to get familiar with that little beast. Okay. Then the transition rates W have been specified as a transition probability from I to I prime. Could be time dependent, but typically it is assumed to be not. And then the different processes that contribute to transition are spontaneous transitions, for example, by trial and error. Then there could be imitation processes where you imitate somebody else's behavior I prime, and the frequency of that behavior is given by that probability distribution. And there could be avoidance processes that somebody else shows behavior I and you don't like to show the same behavior, and that's why you're changing. Okay. So all of that will happen. Somehow we know that these kind of things happen in reality. And then in the special case where spontaneous transitions don't occur and avoidance maneuvers don't occur, but we mainly have imitation processes, then we basically get the so-called replicator equation, which is also often called the game dynamical equation. Replicator equation, do you know it? This describes evolutionary processes in biology. And now we're talking about behavior, so it's something different. In biology, the replicator equation comes out from mathematical laws of inheritance. So there's some genetics behind that, and if you want to learn more about it, then I recommend the book of Carl Sigmund, and there's a fourth power, very nice mathematical book. One of them just wrote me an email today by chance.
We have one question.
Yes.
Conditional probability.
Yes. So transition probability given being there. Okay. A good question, by the way. All right. So this replicator equation basically describes that behaviors, in this case, become more frequent the greater the expected success is. And in biology, we would talk about fitness. In social science, we talk about expected success. Okay? As compared to the average expected success. So if your success, or the success of your behavior is above average, then the frequency of that behavior will increase, will spread. That's basically what that equation over here says, right? The only thing that counts is to be better than average. And then it will spread through. And here, in the context of the social sciences, we don't have genetic inheritance, but instead imitation happens to result in the same kinds of equations, interestingly enough. That wouldn't have to be like this. So in fact, people were using already game dynamical equations, or they were using a replicator equation as game dynamical equations in game theory to describe certain kind of thing, but they were just doing it without a real justification. And then in that paper that I showed you before, I was giving a derivation why and under what conditions it was justified to use that equation game theory. And as I'm saying, the underlying process is an imitation process. And in particular, an imitation process where the transition probability, the conditional, is given by this maximum function over here. So they would not change their behavior if the expected success would go down. That's why we have a 0 here. But if there would be an expected increase in the success, then they would do it, and more frequently, the bigger the success is expected to be, the increase in the success. Okay. That's all. And then, yes?
If you decide the model for one person deciding how can that increase, how do you ensure that another situation that
You need to know the payoffs for that. If you don't have any knowledge about the payoffs, then you can just try it out. And we'll have this kind of situations later on as well. There's still some things that you can do, in particular the win, stay, lose, shift rule. And that basically means that if you've been successful, then do it again, stay where you are, you know, enjoy the success. If you haven't been satisfied with the outcome, then basically move on, try something else. So, and you move on until you happen to be happy, right, with the conditions that you find. And it's an interesting rule, but I guess a lot of people actually do such a thing, approximately, you know.
maybe there's a better solution that you not find it because you just find the local better solution and stop it.
This is according to what people would call satisficing. Most people at least would not necessarily strive for the optimal solution, which might take a lot of effort to find and to implement, but they have expectations about how successful they expect to be. And if they are beyond that threshold, then basically they're happy. And if they don't reach that threshold, then they would still look for a better solution. Okay, and here are actually the payoffs. The expected success is specified over here. So payoff is always referring to if two different behaviors meet, in this case, I and I prime. So suppose you show behavior I, and you could beat other people with behavior I prime, could also be I. And the frequency of such encounters is, of course, proportional to the probability of having that behavior I prime. And you have to sum up over actually I prime, not I double prime. So. All right, it's not a terribly complicated thing. Just we have to plug in those different formulas into each other, and then you get this replicator equation that we also call game dynamical equation. Okay. And one of the things that we can try to understand is the site preference. So why do we have behavioral conventions that people tend to walk on the right or tend to walk on the left, depending on the country? And nobody is telling them. In many countries, people even don't realize that they're doing this separation, just automatic, you know. It's a wonderful thing. There's so many things in life that we don't notice because they're just normal. No? We don't think about them necessarily. And so what I then did, actually my diploma thesis at that time, I was trying to come up with a model to understand this formation of behavioral conventions, and I was formulating it in principle as a coordination game, where there are two pedestrians, 1 and 2, with two possible behaviors, going left or going right, shown over here. And then if both of the pedestrians go to the right, then they manage to walk around each other, and so the encounter was successful, or the avoidance maneuver was successful, and that's why we give a benefit B into the payoff matrix. If one goes right, the other one goes left, then they didn't succeed, they have to try again. That's why there's 0 payoff. Same thing, if one goes left and the other one goes right, 0 payoff, and if both go left, then they manage to walk around each other and there's a benefit, and that's why we have D in here. Okay, so that's the payoff matrix, and this is now inserted in order to determine the expected success of behavior I. And here it is, and then we can calculate the average expected success, and it's given by this. And then if we plug all of this into the replicator equation, then we get this. Now we can factorize it. And so who can read this equation? I mean, what does it say? What do we see immediately? Now, the first thing that people are often interested in is what is the equilibrium solution? An equilibrium solution means there's no change in time. So we set this to 0. And then what are the solutions that basically make the right-hand side equal to 0? Yes? Absolutely. So basically, 3 solutions. One is 50-50. 50% go to the left, 50% go to the right. It seems like the natural solution, you know, like we don't make any assumptions. The one other solution is everyone goes to the right, and a further solution is everyone goes to the left. Now, the next thing that a physicist, for example, would do is to look at the stability of those equilibria. And so what we find is P equals 1/2 is unstable. The 50-50 situation will not stay long over time. If there's some fluctuation, some variability, the system will be driven away from the 50-50 situation into one of those other solutions which are stable. And that is the reason, the instability of the 50-50 solution is the reason that we'll have, in the end, a behavioral convention where everyone is either walking on the right or on the left. And we also understand is why both things actually occur in the world, right? That here, most people tend to walk on the right-hand side, but in Japan, they tend to walk on the left-hand side. And we understand both as possible outcomes of this equation as a result of a coordination problem, which is encoded in that payoff matrix. Yes.
I mean, why in Japan they would have to right?
Well, basically by coincidence, like say thousands of years ago, we all started with a 50-50 situation. And then, you know, there's a little bit of fluctuation. One day, 2 people walk more on the right. And, you know, and then basically the system gets out of the 50-50. And then the system dynamics drives it away until you're close to one of those solutions where basically everyone does the same. So there's a self-reinforcement process that drives the system towards one of those stable solutions. Yes?
Do I understand it correctly that basically someone chooses to write the letter is equally weighted?
Like in the beginning of times, yeah.
But that's, I don't know, I know why it makes sense in a physics way, but the thing is, if you look at it from the social reform, there's actually a very simple explanation why evolution is the way around each time, and that's because of that on the left side. So basically, coming from other traffic situations where the norms, where you don't have norms, but you have rigorous rules how to behave. Maybe those rules are inserted into other traffic situations, such as pedestrian. And most others drive a car or know how to drive a car. Most others would also, for example, bicycle traffic. They kind of already have this kind of norm instilled somewhere. And then in other traffic situations, they would automatically default onto what they would, how they would behave in
Okay, so how long do we have cars? How long do we have cars?
Then the question would be how strong is the influence?
Do you think the lane formation, the side preference were not there before cars were invented?
I wouldn't say so, but it might also be that, for example, which roads you would walk or which side you would walk on might fluctuate much more than, for example, you would observe nowadays. I'm not saying that it is that way, because the counter argument would be, for example, I don't know, like the automatic stair things which have in train stations, and that's good. I don't know what to call it in English.
Yeah, I mean, there are different hypotheses. I think this is important to point out. Different hypotheses that could explain a side preference, including laws, including historical traditions, including the body is asymmetric, and so on. And then as a scientist, you would basically sit down and check those hypotheses, whether they're consistent with empirical findings or not. And I've done that. My personal conclusion is actually the most likely explanation is this one. And I bet you that even before cars were invented, the lane formation and the side preference was there. And someone would have to dig out very old photographs in order to check that. But I would make the bet for a bottle of champagne that would find lanes. And you would also find that in areas of the world that are so remote that people have never seen a car in their life.
There's a comment by Alexander that says before cars we had horses. I think it would say so. It's not like we had no transportation before, like.
Yeah, I mean, in the end, you know, you may have to go into an area where there are neither cars nor horses, and there are these areas in the world, you know, and entomologists, I think that's how they're called, right? Who are basically studying cultures in different areas of the world, and that, you know, that's one of those problems where you could say that's why we need to do that, you know, to understand the reasons for facts of life that determine our life every day. You know, I mean, it's a very interesting question, you know, and I don't want even to force you to take a stance on this. Just I think it's an interesting point in itself that such an equation makes certain predictions, including that the 50-50 that you would probably take as the most natural solution is not going to be out there in the world because that solution is unstable. right?
I'll ask you to ask.
Yeah,
If you can ask.
yeah, please go ahead.
Alexander, do you want to ask your question?
Yeah, so one question I have regarding these sites, does it depend actually on the country, like UK and Japan, where like the traffic drives in other direction compared to continental Europe? Would they have a different preference?
It's a good question, but you may remember one photo that I've shown you in the pedestrian lecture. You still remember? I showed you a picture of London,
Ah, okay,
Oxford
okay.
Street, and I said, "Yeah, do you notice something? Buses go on the left, people walk on the right."
Okay. And
It could still be that it's because in Oxford Street there are perhaps many tourists coming from other countries where they walk on the right, but anyway, I saw that was an interesting observation.
And also one question regarding the model, so like the predictive power of the model. If you would have like enough actors who were told to go on the wrong side, is there like an equilibrium where we can redirect the sites where people go? Like, can we say from like, we need 30% of the flow going the wrong direction, so everybody involuntarily goes also on the opposite side?
See, that is a good student project for the agent-based modeling course that we're giving. Excellent question. Can you induce change? And in effect, there's a paper that goes into a similar direction that I published with Jens Krause, if I remember well, where there was a crowd of people and some of the people got instructed to do certain kind of things to induce something like swarm behavior. But that was more about kind of directional choice and walking together versus going individual. But yes, there are kind of critical numbers of people who can induce certain kind of collective behavior. This much can be said. Also, another important point is that there are building manuals on how you need to specify the capacities of pedestrian facilities, like a sports stadium, right? Soccer stadium, for example. Now, assume you have a building capacity manual for a country that is based on data where all the people are from that country. So everyone is walking, say, on the right, or everyone is walking on the left. However, now suddenly we have all those international sports events where people come from all over the world, and some people walk on the right and some people walk on the left, and everyone thinks it's the right thing to do. Then you will have a lot more attempted avoidance maneuvers that fail, and a lot more disruption and chaos in the crowd. And in other words, we'll need more capacity. You need wider corridors and entrances and exits in order to be compensating for this effect. So that means a stadium that is made for international events needs to have different dimensions, I claim here, than a stadium which is only being used by locals. And actually, I'm not sure they're paying enough attention to this. Again, in the meantime, everyone is staring on a smartphone while they walk, That, again, is changing the capacity of walkways. So in principle, we would have to refurbish entire cities to adapt the capacity to how people behave. They now behave differently, right? And that is a safety issue. It's also an issue of comfort. But anyway, yeah, there's some interesting questions that are related to this. I deserve attention. Let's see questions or comments. Okay. All right. This is always nice to see that this simple thing about site preference is raising so many questions. But you know, you have similar phenomena, of course, when it comes to many other things like clock direction. You know, one day, I don't know how much time it actually took. People decided they go as of what we call clockwise, you know, but in principle they could go the other way. And then there are different writing directions, right? I mean, here we're used to write from left to right, but in other cultures, you write from top to down, I think, right? From right to left, yeah. So all sort of things happen, you know, and you cannot say one is right and one is wrong. All of that obviously is a valid option to do things in a good way, and just coordination among those people who tend to interact more frequently with each other is obviously an advantage, and so we do have that coordination. Now, we can, of course, change the payoff matrix, and then many different games result. And one of the most well-known and extensively studied games is the so-called prisoner's dilemma game. And here we have a situation where it's rewarding to cooperate, but if one of them cooperates and the other one not, the cooperator gets a very bad payoff. It's called sucker's payoff, and the other one gets a very high payoff called temptation. So basically, cooperation is risky and defection is tempting. And so there's a tendency that one of them at least would start stopping to cooperate. And then the other person gets upset too, and you know, both of them will stop cooperating and they will end up with this. It's called punishment. And so in a situation where they could both earn R, the high reward, they would often end up with the poor payoff P, the punishment, or and that would correspond to the tragedy of the commons, you know. So because this time it's not 50-50, which is unstable, so this time it's cooperation that is unstable. And therefore there's a tendency that the system would eventually get into the poor performance state, called the tragedy of the commons, right? And why is it called the prisoner's dilemma? Because police is basically using this trick to make the suspects commit their sins, basically, and say what they've done. I'm promising them that would get less punishment. But in the end, it's a trick to get both of them into prison. Right. Good, and now basically here is the replicator equation for the prisoner's dilemma. And to see here are the different payoffs, we can define the differences which happen to correspond to the eigenvalues, which determine stability. And there are these different cases like a prisoner's dilemma where cooperation is unstable, defection is stable, and therefore cooperation never results. The harmony game where it's just the other way around. Cooperation is stable, defection is unstable, therefore cooperation always results. Then the stick hunt game, you remember it in the very beginning of this lecture. Both cooperation and defection are stable, and the outcome depends on the initial condition. That means where you're closer to. And then there's the snowdrift game where cooperation and defection are unstable, but a certain fraction of cooperation is stable. Okay. And now people are often interested in what if we have a social dilemma, in particular a business dilemma, and can we turn that through social or other mechanisms into another game where cooperation will result? And there are quite a lot of mechanisms, probably dozens or hundreds, but some of the most famous ones are shown over here, based on a paper by Martin Novak, and one of those mechanisms is genetic relatedness, so-called kin selection. Another mechanism is based on repeated interaction. Here we talk about direct reciprocity. You help me, I help you. Then there is reputation-based behavior, also often called indirect reciprocity. So we help the people that have a good reputation. This person helps somebody else, and somebody else helps you. And then there could be network reciprocity, where it matters who is connected with whom. It could be group selection, say 2 different islands. One island on which people tend to be cooperative as compared to an island where they tend to defect. And obviously, the people will be doing better on the island where they cooperate, right? Okay, so altogether, all of this is about how to get from the business dilemma into another game. And here I'm basically showing kin selection tends to shift into the harmony game area. Network interactions tends to shift into the snowdrift game. And the direct reciprocity and indirect reciprocity management tends to move up to the stack house. There's a paper about that in Physical Review if you're interested. And now we're turning to spatial and micro games. Okay, any question? Yeah, please.
Isn't multi-stage business dilemma always converging to cooperation? Or is it always depending on the RS and values?
First of all, the outcome will often depend on the payoff values. Second of all, we haven't talked about multi-stage games over here or iterative games. Here, it depends very much on the strategy that you apply. You will find literature about it on tournaments. Tournaments is the keyword for this. Robert Axelrod was one of the famous people to look into this question early on. And one of the strategies that turns out to be particularly doing well is tit for tat, and basically do what other people have done to you. So if they were nice, then be nice. If they were nasty, then be nasty. And it's not the only strategy that works, and it doesn't work always, but it's a strategy that is actually doing pretty well. And still until today, one of the most remarkable strategies. Okay. Now we're looking into spatial interactions, and here the interesting finding was that while if everyone interacts with everyone else, or if everyone interacts with randomly chosen people, in the prisoner's dilemma situation, you would end up with defection only. Total disaster, everyone is nasty, everyone defects, tragedy of the commons. Not so if there is a spatial interaction where people imitate the best performing behavior in their neighborhood. Here, surprisingly, cooperation shown in blue, defection shown in red, yellow are the changers. Surprisingly, cooperation can survive. It's not a high level of cooperation, but still suddenly can survive based on local interactions. You know, and somehow we know from the village that people behave differently. It's a local interaction effect that makes people behave differently. And we have extended that. So basically we have assumed a square situation where not all the grid cells were occupied, but there were some empty ones. And then basically people could migrate to empty cells, and they would do it in a success-driven way. Within a certain radius, they would check out empty sites and would make test interactions to figure out what are interesting or attractive sites, and they would move there. Okay, so they would migrate. And before we go into the combination of behavioral change and migration, let us look into the migration only case. With different payoff matrices. So basically here we just have a one-dimensional lattice, not a two-dimensional one. And people can move right or left. And I will do so based on what would be increasing their payoff. And we start, we assume two different kinds of behaviors. We start with a situation where both behaviors are equally distributed and homogeneously distributed in space. There's a little bit of noise as well. And now, one interesting observation is that for many payoff matrices, you would find a pattern formation. That means this homogeneous distribution would not stay forever. Rather, you would find different outcomes. There could be segregation, like in the lane formation. There could be repulsive agglomeration, like in a ghetto formation scenario. It could also be attractive agglomeration, like in a clustering scenario. And that would very much depend on the payoff matrices. Yes?
Right, people on each side, they move also like feeling the other one, or just feeling some kind of external dimension?
They're just feeling interactions at that location with the other.
Yeah, like,
With all the people in that same cell. In this case, we allow a cell to be occupied multiple times. Right, and you can see that basically starting with a homogeneous initial distribution, we would eventually find something very different. So there's better information of a collective behavior that depends on the payoff matrix. And so if we look into the parameter plane, where we change P and S, that these were two of the payoffs in the payoff matrix, then everything which is shown green will show pattern formation. Only in the red area over here would the homogeneous distribution stay over time. And those areas can be calculated analytically, so we know why this is happening and where this is happening. It's always a nice thing, you know, if you can make a calculation and make a prediction and the prediction works. even though the calculations often make simplifications. So, all right. And then we have been asking ourselves, what happens if we combine those two different things? Behavioral change according to a payoff matrix and success-driven migration. And it was by coincidence that we looked into this, because I had done the traffic modeling before that was about mobility. And then I started to get more interested in game theory, and I thought, okay, what happens if we combine the two? And actually, I didn't have any expectations. Actually, I thought most likely nothing is going to happen. Those two things, like behavioral change and spatial change, will just be independent from each other. That was my expectation. But I thought, okay, it's interesting enough to look into this and see what happens. So do we have any expectations? So you see, we basically start with 50% cooperation, include 50% defection in red, and some empty spaces. And initial condition is always the same. Here we will look into imitation only. Here we'll look into migration only, and you will combine the two. What do you expect? I don't know, you have to take a bet. Just take a risk, you know, it doesn't have to be right. Just, okay, what do you expect?
The imitation migration and the islands.
Ah, come on, you have to look that up. No. Ah, you're a genius, okay. Yeah, nice prediction. So, what? Any further points?
In the chat, it says, the right side more structure.
Here, more structures. Yeah. Okay. Oh, we have too many geniuses in this course. It's a great thing to have. Okay, good. So look what happens. So imitation only. The amount of red increases, that means defection spreads. Okay. In other words, cooperation goes away. Partly, at least, right? Now migration only. So how much cooperation will we have after some time? This is more a tricky question. And this does not include any behavioral change, right? Just including location change. So level of cooperation stays the same. Okay, here we go. Looks different, but both of those approaches cannot increase the level of cooperation. So both approaches fail to increase cooperation. Now, if you combine two failing approaches, what do you get? Cooperation, you say. It's like the most natural thing, of course, but yeah, some people have seen it coming. And in fact, you know, it's you find these large islands of cooperation surrounded by the factors who want to exploit those cooperators, but still cooperators run away from those defectors and manage to establish those cooperative islands where they have a good life for quite some time. Okay, and I showed that to Ernst Fehr, who's a very famous economist and game theoretist, and said, well, what if one of those two people one of those cooperators decides one day to wake up and to be a defector and exploit everyone around them, all the cooperators around them, you know, wouldn't that basically erode cooperation from within? Okay, I went home. I saw how smart he is. And then we basically had to look into these kind of scenarios, right? And so that's what we did next. If yeah, the third thing, I mean, the first two didn't change anymore because there was no noise and basically the situation froze. The third one, the imitation combined with migration, I think keep changing as long as I have observed it. Yeah. Now we are adding noise, so things keep changing anyway, but not necessarily a lot. So like with 1%, people are doing the opposite of what the game theoretical rules would otherwise say. Okay, and we're looking at different kind of noise. One is noisy behavioral change. And this is what you see over here. And starting with cooperation, we end up in a very sad outcome, which is kind of defection by almost everyone. Tragedy of the commons, right? As we expect, you know, I mean, Ernst Fehr was right in a sense. And then we looked also into the effect of noise in space. And you know, people make holidays or they go to other countries to study, and you know, that didn't really improve cooperation. But we don't combine imitation, migration, and noise. And that's what we're doing over here. And so basically, I asked my PhD student at that time to run a simulation starting with defection only. To make it more exciting, I thought. So kind of hell on earth, that's kind of the initial state. Homo hominis lupus, as St. Thomas Hobbes, is that what it's saying? I think it was saying, like people are like wolves to other people. Like that was his imagined original state of the world in the beginning, many thousand years ago. And then, okay, a bad world where everyone cheats everyone else. And then the question is, would we manage to get cooperation eventually? So I told him, why don't you simulate that? And then I left his office, and a week later or so, I came to visit, and I asked, what did you find? And he more or less said, well, actually, to be honest, I didn't do that simulation because I thought it was a waste of time. And why should I waste my time? Therefore, okay. And I said, well, but I'm really interested in this. Couldn't you do me a favor and just look into this? It doesn't take so much time to change some parameters. Okay, so I left the office. A week later, I came back, and still the simulation was not done. And I said, okay, let's do it together. You know, so I was taking a chair, we were sitting there, he was changing parameters, and then for some time, nothing happened, basically. It was stayed red, like a lot, oops. Trying to avoid the discovery. Okay, so here we go. Just a dispersion happened, right? Because of the spatial noise. And it went on, it went on. We had a cup of tea and a cup of coffee and so on. And then eventually, after 25,000 iterations, something happened up there in that corner where by coincidence, there were a few people who cooperated. And once that happened, a supercritical cluster of cooperation had occurred by coincidence, then cooperation spread. And it spread quite quickly throughout the entire world. And I'm still waiting for this day. I want to still experience that day in my lifetime. Because I believe it's going to happen. We're pretty close. Okay, and then I went to elsewhere and asked him, what do you think about it? And he said, well, interesting, but isn't that a green beard effect? Do you know what the green beard effect is? Like there are signals that people send, and who is knowledgeable to read those signals, you could know that this person would cooperate or not, right? And he said, in your rules, we've assumed that people make test interactions, check out the neighborhood, what they would earn if they were there, and then they moved there after knowing that. Of course, the neighbors could change their behavior too. So it's no guarantee that neighbors would behave the same way in the next round, but still, it could be indicative. And I said, okay, so let's get rid of the green beards. And now we're coming to this win-lose, win-stay-lose shift. So basically, yes, please. Yeah, please. Could you ask your question?
Yes, there is a good video I posted in the beginning of the lecture on cooperation and the social dynamics. And it's about also greenbeard altruism. The link is on Zoom. Maybe I could send it to you. There's a really good video that explains it.
It would be fantastic to share it with everyone, but also if you could send an email to me, it would be very much appreciated.
Yeah, it's a guy who does simulations, and it's really well explained.
Okay, great, thank you. All right, so basically what we do here, we now look into, again, spatial interactions with migration, but we assume that people can't see the behavior of other people. We just say that if people are satisfied with the payoff they get locally, they will basically do the same thing again. They stay in the place, they play the same behavior. If we're not satisfied, they would either move on or change their behavior or both. And the expectation that they have would correspond to a certain percentage of, I think, the maximum payoff that they've received within a certain period. So basically, people are successful, they do the same thing and stay, and otherwise they move on. And this is the dynamics. And what we find is we still get these cooperative clusters surrounded by defectors, but the cooperative clusters are not anymore that big. Still, there is a clustering effect which is beneficial for cooperation. That clustering effect is a result of that ability to migrate to show success-driven migration. Yes.
Like always that people don't see the other one. I mean, like say it's satisfied somewhere, but it kind of somehow feels also the other one is now maybe not like from the
We're not talking about realistic situations here. We're talking about abstracted scenarios where we're interested in learning what would happen if people didn't know this or didn't know that, or just have this information or just have that information. So what we want to know is how much information do we actually need in order for cooperation to survive or even spread. And that very much depends on, for example, also the payoffs, right? Now, what you do when you go home after this course, now how you apply those learnings in your real life, considering all that information that you have. You may want to tell me one day if that succeeded, but yeah, please make use of the information that you have, sure. But
There is one question.
abstraction, simplification is part of the scientific method.
And Jan mentioned that in the lecture regarding traffic, we learned that traffic breaks down if people are left to cooperate. Why is it that cooperation working for?
Traffic breaks down if people are asked to cooperate. I don't get the point. Do you want to ask a question, please?
Yeah, so we had this traffic light simulations or crossroad simulations, so to say,
Right.
where there was different scenarios, and there was a scenario where people, there was no traffic light, but people could kind of cooperate, so to say, so either let someone pass or drive through. So which was, for me at least, kind of like cooperation, where they, so people were optimizing themselves, so to say. And I kind of assumed that there should be like a cooperation scenario there, but we learned that this works pretty well for small traffic flows, like when the roads are kind of empty. But then there was a threshold where it nearly exponentially went up, and basically then the traffic flow decreased to zero, so to say. And that's what I meant, like people were allowed to cooperate, but we learned that when there are a lot of people to cooperate, it actually does not work. That's what I meant with the question.
We'll find something similar over here when we come towards the question, how does the networking matter actually for the outcome? But yes, our traffic light control approach has been pretty much inspired by some game theoretical thinking. And so the idea is that if you have suitable interaction rules, then a favorable outcome would result by itself. If you have bad rules of interaction, then things would go wrong. And you will have traffic jams, you will have non-cooperative outcomes, and tragedy will be comments and so on. So everything is about finding good interaction mechanisms that would do the job for you. And that's called mechanism design. And so we're trying to find some mechanisms now that work and can establish cooperation, right? Okay, so we did that simulation, and we published it in PNAS, and then I went again to Ernst Fehr, and he said, okay, and I think he was still not entirely believing it, but it was kind of convincing enough for him that he said, okay, let's try it out, because he was a behavioral economist. And so he was interested in how do real people behave. And of course, they could behave differently from the idealized assumptions that we've made in the computer simulation. So two people of his team, Charles Efferson and Sonia Fogg, were doing an experiment with us, Carlos Roca and myself, who had written that other paper. During an experiment in this building, A level is a laboratory where things happened. And so basically there are 36 cubicles, and there are people were represented by one of those occupied places. We didn't show anybody whether those people were cooperating or not. Every person was shown in the middle. There were certain migration radius and certain interaction radius. And then we were looking into what was actually happening. And then to the surprise of the behavioral economists, I would say, we found that migration really fundamentally changed the outcome. So without migration, cooperation went away over time as expected, but with migration, success during migration, the level of cooperation could be sustained over a long time. So mobility could prevent the tragedy of the commons. And also we found that migration allows cooperators to avoid exploitation. So, you know, we had better payoffs on average. We also found that migration allows cooperators to form cooperative neighborhoods. And we found that mobile cooperators seek smaller groups. That was a matter of the payoffs that we assumed. And we found that mobility was key to success in that experiment. Right? So, okay, I mean, some people don't like migration, but it may have actually also some favorable side effects. It doesn't mean that it's not a political challenge. But anyway, scientifically, I think that was an interesting finding. And it's not the only mechanism, of course, that can support cooperation. But another surprising finding is actually that networking people more and more is not necessarily good for cooperation. I'm not an enemy of globalization at all. Just the question is, how do we do it right? So what we assume will be here is that people interact with their neighbors in a circle, very artificial scenario anyway. And it turns out that a lot of cooperation results, as we know that from villages. So neighborhood interactions are good for cooperation over here. And then we add additional connections to other people randomly, more and more. And now for some time, cooperation stays on. But then comes the point where suddenly a lot of defection wins through. So too much connectivity apparently is not good. And we know why, because that situation is described by the replicator equation. And the replicator equation predicts in the social dilemma situation the tragedy of the commons as the outcome, right? So no cooperation at all. And that's what we find if everyone gets connected with everyone else. We also find that if everyone randomly interacts with other people. But we don't find that if people do interact primarily locally and with some, not too many, other people from any place of the world, right? So in fact, as we add long-range connections, it's good in the beginning, because it increases cooperation. So we would reach out to other people long distance more and more, and it's good. You know, so we would keep doing that, but there's a point where adding more long-range connections could actually be detrimental. And it's kind of unexpected, because I think most people would not think that this would happen. I guess many politicians don't know about it. Many scientists don't know about it, but it's a fact that can be shown in computer simulations and also understood well analytically. So globalization is a good thing, but if you do it wrong, there could be problems. And now the question is, what can we do in order to avoid that cooperation would break down if we get more and more connected with more and more people all around the world? And some people have suggested that punishing non-cooperative behavior would be a solution. It just doesn't feel good, right? And this paper over here is about looking into punishment effects. And we're basically now assuming 4 different behaviors. One is cooperation, one is defection as before, but then there's another one which is cooperation plus punishing defectors, which is costly, it takes some effort, and then there's defection plus punishing defectors, even though people are defectors themselves. That's why we call them immoralists, while the cooperators who punish we call moralists. Okay? Now, if we simulate that, in a social dilemma situation, everyone interacts with everyone else, and what we find is immoralists disappear quickly because they have a high cost, and the moralists disappear quickly as well. And then we basically stay with cooperators and defectors, and we know what happens then: a tragedy of the commons. So it means defectors win through, and we have a tragedy of the commons. Okay. But now we play the very same game, just with the difference that we assume that people would interact with their neighboring individuals only. That means I think that was the 8 people around them. And we start with 25% of each of those different behaviors randomly distributed. And what do you think will happen? Yes?
Moralists would win.
Why that?
Overcome the cooperators.
Yes?
Maybe because if you're in the deal, it's not as costly as if they have to deal with the in the whole system. So they have a better chance to survive.
So what we'll find is, okay, I'll play it. There are different phases in this game. In the beginning, it really looks like this is going to end very badly. So red wins through initially. But then after a short time, no, it's green and blue that dominates. And in between, they're separated by red. And this is important actually for the outcome. Why? If we would just have cooperators and moralists next to each other, the cooperators would crowd out the moralists because the moralists have extra costs to pay for the punishment. But if they're separated by the defectors will crowd out the cooperators, as we know, but the moralists can punish the defectors, and that's why they succeed. So, no, actually, you wouldn't think this, but the problem for the moralists are the cooperators. It's kind of unexpected, right? The moralists cannot handle the cooperators. And the bad people, you would say that those that don't cooperate, that help somehow the moralists to win this battle. Kind of unexpected, so unexpected that in fact, another highly esteemed colleague was doubting this result. I presented that during a summer school. And then in the evenings, he was actually programming this by himself to check the result. He couldn't believe it. And I think it took him 2 or 3 nights to program this. And he said, "You're right." And that was, of course, a very nice experience. It also showed that somehow the result was unexpected, because now we get really the opposite outcome from what we would get if everyone interacts with everyone else. And that's often a simplification made in economics. We call this the representative agent approach, where you assume that an individual acts with a kind of soup of people, an average behavior. And this simplification gives a totally different outcome from what we observe in this spatial interaction situation, right? So the representative agent approach, which is used a lot in economics, could be very misleading about what would happen in the real world if not everyone interacts with everyone else. And in fact, there could be many different outcomes, as you can see over here, depending on parameter combinations. So this is really a pretty funny game where you can have many interesting findings. Yes?
I was kind of wondering why are there still some differences especially this number? Because if one that about a lot of neighboring lawyers, the kind of punishments or the cost for the punishments are shared among the
I think one of the reasons is that there's some noisiness in the specification of the imitation in that particular paper. And as we've seen before, noise can sometimes be good. Like when we had this outbreak of cooperation in a bad world, started all red in the beginning, remember this. If there had been no mutation, no randomness, cooperation could have never emerged. So, making mistakes sometimes can allow things to happen that we just wait long enough. It could be ending in very good outcomes. And this is how evolution works, right? Mutation and selection. Mutation is the remnant part. Selection is those solutions that happen to result from mutation will be multiplied more often and spread more quickly. Okay, I think.
There's a question in the chat.
Yeah.
About the slide. Too much connection is not good.
Yes.
And the question is, does free riding show its effects? If everybody is connected, everybody relies, that others will do something for them.
Yeah, I think this is a way of describing how basically cooperation erodes. Yeah. All right, I think we're at the end of this lecture. I did it a bit more slowly today, also because I think we have more time this semester. So we'll see whether I can have an additional lecture about the second part. But I very much really enjoyed the very interactive way of lecturing today. So thank you very much for all your questions and feedback. You're comments, your suggestions, your knowing what comes out or guessing what comes out. I think it's a lot of fun. And I hope you enjoyed this lecture. Have a nice evening.